Hi, welcome to my talk on windmill of the minds and an algorithm. My name is Hing from Australian National University. Today, there are three topics. First, the sum of two squares. Here are the primes 2, 3, 5, etc. The only even prime is 2, which is equal to 1 plus 1, a sum of two squares. How about the odd primes? There are two forms, 4k plus 1 and 4k plus 3. They don't have names, so I give them names, tick and talk. 3 is a talk prime, 5 is a tick prime, etc. And as you can see, a tick prime can be expressed as a sum of two squares. Here are some more examples. Now think, if you have an odd number which is equal to a sum of two parts, one part must be odd and another part must be even. So the examples suggest that a tick prime is a sum of two squares, odd and even, uniquely. Here, this particular symbol means that this theorem has been formalized, has been proved in a computer using a theorem prover. My theorem prover is HOL, which stands for higher order logic. And the following is the mathematical expression of the statement of the theorem. This is first given by Fermat, and he claimed that he had a proof, and he challenged others to offer a proof. Nearly 20 years later, no one offered a proof, and so he gave a hint. This is very rare if you know the stories of Fermat. Then, a century later, almost, Euler worked out the proof on and off for 7 years by using the hint. And other mathematicians, famous mathematicians, also give proofs. Why? This is because they found that the previous proofs are too complicated, and they actually invented their own theories to give their own proofs. And there are still more. Now, I don't know all the stuff for these particular proofs. So what do I know? Well, I know the windmills and the mines. Recall that a tick number is equal to 4k plus 1 for some k of that particular form. Now, 37 is a tick number. And so let us try to figure out a shape for it. So we express 37 as 1 plus 4k, k being 9 in this case. The first one is 1 times 1, and the 9 is 9 times 1, which can be expressed as a square and also 4 rectangles in this form, all right, which is a windmill. And note that by 9 times 1, I mean horizontal 9 and vertical 1. Here is another picture for the same number. Because 37 can be expressed in another form, the 9 can be factorized as 1 times 9. And so we can get another windmill of this particular form, which then the 1 times 9 means that I have horizontal 1 and vertical 9. So a windmill is just a central square with 4 identical rectangular arms. And I am going to use an expression, windmill x, y, z, which is equal to x squared plus 4y, z. And they can be of various forms, right, depending on the relative size of x, y, and z. And I shall use a triple x, y, z to just represent a windmill. And x is the length of the square, central square. Y and z are the horizontal and the vertical of the rectangle on the top part of the central square. And these 4 arms are arranged in a clockwise manner. So every tick number will have at least 1 windmill, there may be more. And so what we want to know is how many windmills for this particular number 37. Well, recall that n is odd, and so x squared itself must be odd, and so x must be odd also. And then we can compute the difference, like in this table. We just use successive odd x and try to factorize the product y and z. Right? This basically will give us all the triples that correspond to the windmills. All the windmills of a number form is mills, and which is a set. And in this case, the particular set contains all the triples above. And if you count them, there are 7 elements for this particular set. And in pictures, these are the windmills, 7 of them, right? And for the mine, we shall come to that very soon. First, we want to pair the windmills up by what I call flipping. That means I'm going to flip the rectangle. If you remember, this is 1 times 9, right? And I'm going to flip it to 9 times 1. And so 1, 9 and 9, 1 will be a flipping pair. The same for this particular 2 triples. 1, 7 and 7, 1, they can be paired up by flipping. And the same for this pair, 5, 1, 3 and 5, 3, 1. The last one, basically because the arm itself, the rectangular arm itself is a square. So flipping is just itself. This is called a fixed point. This is the expression for the flip mapping. X, Y, Z becomes X, Z, Y. And if you flip twice, it comes back to the original. And so we call this an involution. And any fixed point of this flip map has this form, X, Y, and Y, the last 2 components being equal. This is an example. And whenever we have this situation, then the windmill expression becomes something like this, which basically becomes a sum of 2 squares. And so any fixed point will give a sum of 2 squares. What is the mine? The mine is the biggest heart of the overall windmill shape, like this. This is a windmill, and if you get the biggest heart in red, then it goes to another windmill. So a windmill can transform to another through the mine. We can take from left to right. If we go from left to right, then it is expanding the central square, but shrinking the arms. If we go from right to left, then it is the opposite. All right. And if we define the mine of a triple equal to the length of the side of the red square, this is the expression if we use simple geometry. Don't worry about it. All we want to know is that there are 3 cases to express the mine. Okay. Now, what we can do is we can pair things up by the same mine. All right. And for example, these 2 got the same mine, and so we can pair them up together. These 2 got the same mine. All right, we can pair them up, and these 2 also got the same mine. This one, as you can see, the mine is just a central square, and so this one is fixed by this particular mapping. I use the zigzag symbol for the pairing because it actually is first given by Segia, and there is an expression, right? And we shall see what the expression is in a moment. But you can see that if we do the second map once and second map twice, then basically we go back to the original. And so this is an involution. And any fixed point of this Segia involution is of this form, X, Z, the first 2 components being equal. For example, that particular windmill. And this is a fixed point because the mine is just equal to the central square. So a map that can undo itself is what we call an involution. And an involution will look like these things will pair up. Like this point go to the other point, and then it has to go back. And so pairing, pairing, pairing. What about the last one? Well, it must have paired up with itself because there's nothing for it to go to. And all these are the fixed points. They form the fixes of the particular set. And for a finite set, we have this theorem. And that is because all these parts got an even number. And so the number of elements for the overall set, if that is odd, that means there is an odd number of fixed points. And from this theorem, we can see that for any involution, if there's only one fixed point, then the size of the overall set must be odd. On the other hand, if the size of the overall set is odd, then it must mean that there is at least one fixed point. And actually, for a tick prime of this form, 4k plus 1, we can show that there is only one Segier fix, and that is the 1k. And because of that, the size of the set, mu's n, is odd, and therefore the fixed point exists. And if you remember, a fixed point will give us a sum of two squares. And this is the one sentence proof given by Segier. All right. All you need to know is that this is the expression for the second map, and it got three cases, basically from the three cases of the mind. And if you look carefully, you can see only addition, subtraction, and doubling. And so it is a very simple way to do the calculation. Okay. Now, all these actually has been formalized and been done in other theorem provers. So what is new for me? Well, this is the two squares algorithm. That means I'm going to find the two squares for the tick prime. What we can do is, once we got all the windmills of a particular number, we can start from the non-Segier fixed point, which is 1k, say from here. And what we can do is we can just flip it, right, to get to another windmill. And then we try to use the same mind to pair it up to go to the next one. And so we do a Zeta map, all right, and then we can go to a new windmill. We basically repeat the process. We flip again, and we do the Segier again, flip again, and Segier again, and then we arrive at the prefix point. And so this will give us the sum of two squares. And for the algorithm, this is the input, a tick number of this particular form, and we want this output a fixed point for the flip map, which is of this form, triple of this form x, y, y, so that we got the sum of two squares in this way. And the flowchart is like this on the left, and the pseudocode is on the right. Okay. As you can see, flip is very simple. Segier is also very simple. And so our algorithm is also very simple. And if the number n is not too big, this algorithm actually is quite fast. Of course, what we need is we need to show that the code is correct, and actually it will terminate for a tick prime. We just try to see some sample run. And in the theorem prover that I have, I can just use this EVAL for evaluation. And once I define the algorithm in the theorem prover. And so by evaluating it, I shall get the triple, the pair, 1 and 6, right? That means 1 square plus 6 square is equal to 37. And by prefixing with a time, we can actually show the time taken for the execution. And here it is just very fast. Here are more examples. For 97, it is still fast. For a bigger number, it takes 2 minutes. And for a 10-digit number, actually 11-digit number, it needs 6 minutes, right? Actually, all this evaluation is by symbolic arithmetic, which is order of magnitude slower than the native code. So it is quite impressive. For the correctness of the algorithm, you do have to read my paper all right, and basically the proof involves permutation by involutions, and also the permutation orbits, and also the orbits connecting fixed point of one type to fixed point of another type. All right, that's all for today. Thank you very much.
Okay, so that thanks the speaker. All right, so we have the speaker there to answer our questions. I don't see any
question.
Really, everyone just want to get a dinner, I guess. Oh.
So do you have a termination proof, and do you know what the bound or the expected runtime is?
Oh, the expected runtime of the algorithm. Well, it actually is quite hard to get a definite estimate of the upper bound, but I would say that it is not in the range of a polynomial time algorithm. It actually is an exponential time type of algorithm. So if you read the literature, there are actually much faster algorithms to get to the or try to express the take prime as a sum of two squares. But those algorithms are actually quite difficult to implement, right? Not as simple as the one that I have presented. So there is a sort of trade-off, right, of whether you want a fast algorithm, which can be quite complicated, or whether you want a simple algorithm like what I have done, and just use the algorithm to work on, numbers that are not 20 or 100 digits. Like my example, 10 or 11 digits, 12 digits is quite good for simple experiments.
Okay, thank you. All right. Any other questions? I do want to add that I believe the polynomial bound of that efficient algorithm depends on Riemann hypothesis, but could be wrong.
Yeah.
Extended Riemann hypothesis. Oh, it's on Wikipedia.
Well, what happened is that the things that I have presented is actually quite simple, as you can see. But the actual proof of the Fermat two-square theorem can involve some very deep theories, like Gaussian integers. And if you have that kind of knowledge, right, using complex numbers, then there is something called Euclidean algorithm on those complex numbers, right? So by using that kind of idea, you can actually get to a very fast theoretical algorithm to find two squares for the take prime, right? But in that case, as I said, you have to have at least complex numbers, implemented, which of course is not that particularly difficult. There are books on that particular part, and so for those who are interested, just read the references in my paper. And I think there is one reference pointing to a very clear explanation of what the author claimed to be the fastest algorithm, right, to find the two squares.
All right. Okay, I don't see any question. Final round question call. All right, if there are no more questions, that thanks the speaker again for this.
Thank you very much.